Okay. So I wanted to add a couple of remarks. First of all, indeed, I put here the soft. And remember that the covariant derivative, of course, is the ordinary derivative. And the ordinary derivative produces the residual momentum K, which I assumed would be a soft momentum. But it also contains the gluon field and the photon field, as one of you mentioned, but let me ignore photons for the purposes of this talk. So this is the gluon field. And of course, gluons can be hard gluons and soft gluons. Gluons can have any momentum. Okay, we integrate over d4k, of course, when we do Feynman calculations. Now, we derived this by... Good, I will try. So we derived this by integrating in the functional integral over the field capital H. Now, this was a Gaussian integral, but of course, if you include the gluons, it's no longer a Gaussian integral as far as the gluons are concerned, because the gluon Lagrangian itself, the Young-Mills Lagrangian, is not linear. It has triple gluon couplings and quadruple gluon couplings. So basically, you know, we cannot perform the path integral over all the hard gluons, which would be there. So we are ignoring the hard gluons for now. We put them to 0 by hand, and I'll tell you later in this lecture how to account for the hard gluons. When you wanted to account for the hard gluons at the level of the functional integral, you would find integrals that nobody knows how to evaluate. So that's the first comment. We'll just keep the soft part of the gluon field here, and that's the correct answer, and I will justify this a little bit later. And then I also noticed that not everyone was familiar with functional integrals, and that's also fine. You don't need to know them for the purposes of my talk. Let me show you a more pedestrian way to derive this result. You remember that we had an equation where we had a term here which had 2 little h's and 2 capital H's, and then we had terms which were mixed. And one thing you can do is at tree level, that's always allowed, you can start from this Lagrangian. If you want to get rid of a particular field, such as this capital H, you can do the following. You can derive the equation of motion for this field. You can solve this equation if you can, and you can plug the solution back in to the Lagrangian and see what you get. This is a way of integrating out a field at tree level. And let me just show you that this way you get back the same Lagrangian. What you would do here is right up there. You take the variation of the Lagrangian with respect to H bar, capital H bar of V. That has 2 terms, this one and this one. And you set this to 0, basically, because there's no term containing a derivative of H bar. So we have to set this variation to 0. And there's essentially 2 terms. The first term is minus I V dot D minus 2m H, capital H. And the second term is I D slash perp times little h. And we set this equal to 0. And we solve for capital H. And the solution for capital H, if we do that, is capital H equals to the inverse of this differential operator, 2mq at I v dot b soft times I d soft slash perp times little h. So we get a solution for the lower component fields in terms of the upper component fields involving this inverse differential operator. Now, inverse differential operators can be subtle. You have to worry whether they really exist, etc., etc. But you see, in this case, it's relatively simple because this is a soft derivative, so it counts like lambda QCD. Here we have the inverse mass, which will tend to infinity. So you can always think of this inverse derivative in terms of its Taylor expansion in a geometric series, and then each term is well defined. And you see that this capital H field is 1 over mb suppressed relative to little h. So it made sense to integrate it out. It's a power suppressed correction anyway to the field. So the little h is what remains of the heavy quark field in the infinite mass limit, and therefore this was a good choice for an interpolating field. And if you take this solution, and you plug it in here, you get exactly this. So I leave this as an exercise. So plug in and rederive. Let's call this star. I leave this as an exercise for you. Good. This just to finish the first lecture. Now, you know, if you would do a long course on the Wilsonian operator product expansion, you would learn that when we integrate out heavy fields, heavy quantum fluctuations, we first generate an effective action such as this, which is non-local. And then we can expand this non-local action functional in terms of local operators. That's exactly what's called the operator product expansion, okay? So in what sense is this action non-local? It's non-local because it has derivatives in the denominator. So an equation which has a derivative in the denominator is always non-local because this inverse derivative is always defined through some Taylor series, and it's an infinite series. And if you have an expression with an infinite number of derivatives, it's the Taylor series of a function that's non-local, right? But you see, this is a small non-locality. It's a small non-locality in the sense that the derivative is of order lambda QCD, and you must compare it with twice the heavy quark mass, which dominates here. So when you expand this in powers of derivatives, you get terms having more and more powers of 1 over m and more powers of derivatives upstairs, okay? And then it becomes a local expansion, but infinitely many terms. This is like Fermi theory. If you ever learned Fermi theory, W exchange, effective for fermion interaction, the W is a heavy particle. The non-locality there is on the scale 1 over mw square, which is what we call the Fermi constant, GF, okay? And we are very familiar with that. We expand out this non-locality, we get an infinite series, we truncate at the leading term. And we're going to do the same thing here. So we can expand out this non-locality very simply in HQET, simply by using that if we have this inverse soft derivative, we just use a geometric series here. We write this as 1 over mq, sum from 0 to infinity of minus I v dot d soft over 2 mq raised to the power n. And you should think of this as lambda QCD over 2mq to the power n. So you see, this is what we call the heavy quark expansion. When people talk about heavy quark expansions, they always mean expansions in powers of lambda QCD over the heavy quark mass. Yeah, I'll derive it in a little while. By the end of this lecture, the soft gluons will, yes. I mean, you will see that what is not surprising that for consistency, the soft gluons will have the same power counting as the soft momentum. Otherwise, it would not make sense. But I will derive that retroactively in a moment. So I think this part, is clear. By the way, we have an explicit solution for capital H. So it's not that anything is lost here. If at any stage you wanted to reconstruct the original psi spinner, you just add little h and capital H, for which you have this expression. And you use this expansion and you get the power series for the original psi field. So it's not that any information is lost. It's just organized in the form of a heavy quark expansion. But let's look at the leading term. Let's start from here and insert the expansion there. Then we get for the effective Lagrangian, the leading term, little h, I v dot d soft, little h. And then you see already the next term has this 1 over 2 mq. And then it's the n equals 0 term in this expansion. So it will be little h id slash perp, id slash perp, little h. And the next term will already be 2 powers of mq down. Okay. So by the way, I'm not giving really citations here, but of course this construction was done by Howard Georgi in Physical Letters B 1990. So this is one of the classic papers of heavy quark effective theory. Now, if we really take the infinite mass limit, so the heavy quark limit, we set lambda QCD over MQ to 0, or if you wish, MQ to infinity at fixed lambda QCD. Then only the leading term remains. So strictly speaking, HQET, the Lagrangian in HQET is only the first term. And this you can split up into the kinetic term. It's just the ordinary derivative, and then the vertex, the quark-gluon vertex, which is V dot A mu A T A for the soft gluon. And of course, from such a Lagrangian, we can derive Feynman rules. And these Feynman rules are very simple. We have a propagator and we have a quark-gluon coupling. And the propagator, you remember, is the Fourier transform of the inverse of the differential operator between the two quark fields. And the rule for the vertex follows from here. And what is conventional is that these heavy quarks in HQET, they are drawn as double lines, not single lines. So we draw a double line. The double line carries the velocity as a label. And remember, the velocity was the velocity of the meson containing that heavy quark. So we are always in the context of describing the properties of heavy mesons. And then the momentum flowing through this line is the residual momentum K. And what is the rule for this propagator? of the heavy quark. Well, it's the inverse of this in momentum space. The derivative produces minus I times the residual momentum. Minus I is cancelled by this I. So we'll get V dot K from here. And the propagator is I over that. And then there's the Feynman I epsilon, which I need to add. So this is the propagator. And then the vertex, we have a heavy quark interacting with the gluon. The heavy quark carries again the velocity v as a label. It has a momentum k and k prime. The gluon is soft. The residual momentum is allowed to change. The velocity is never allowed to change. The velocity is the meson velocity. It's stuck. And the rule for that, and here then the momentum would simply be k minus k prime. Okay. And Lorentz index mu, polarization index mu, color index A. The rule for that is I times whatever we see here. So it's I times strong coupling GS, V mu TA. This is the vertex. And compared to QCD, the key difference is that we have gamma mu here, 4x4 Dirac matrix. In QCD, we simply have the trivial velocity vector there now. And the propagator, well, has this funny linear structure. It's a linear propagator. Normally in relativistic QFTs, we have quadratic propagators with two solutions. When you set the propagator equal to 0, the poles, there are two poles, right? Opposite side of the contour. Somehow, this is the non-relativistic limit in some sense, where only one solution remains. Actually, another exercise that is useful to do. Exercise is to derive the propagator starting from QCD. Basically, take the QCD propagator for a massive quark, consider the quark to be close to its mass shell, and simplify, and you should find this result. Now, there's a symmetry of this Lagrangian, which is, as I mentioned earlier, not there in the full theory, not there in QCD, or not manifest in QCD. What is the symmetry? Well, the symmetry is almost trivial. So when people first wrote papers about it, we thought, okay, this is so simple, can you really write a paper? But it's it's a little bit profound. Because the first part of the symmetry, this is called heavy quark symmetry. The first part of the symmetry is that the mass of the heavy quark does not appear in this Lagrangian. So this Lagrangian does not know anymore in the infinite mass limit that I started, say, from a B quark. It's simply, this information has disappeared. Of course, it's here in the second term, it's there. But in the limit where we send m to infinity, it's gone. Okay, so it really means top quarks, B quarks, charm quarks, they're all described by the same Lagrangian in the heavy quark effective theory. And that means there is a flavor symmetry. So there's a flavor symmetry. We are familiar with flavor symmetries for the light quarks. For the light quarks, it's the opposite. We say the quark masses are so small compared to lambda QCD that to good approximation, we can send them to 0. And once they're 0, it's the same for up, down, and strange, okay? It's kind of a trivial flavor symmetry. Here it's more profound. I mean, the top and the bottom differ by a factor almost 40 in mass. And nevertheless, the mass has disappeared here. Their bound state would be described by the same physics, even though the masses can be hugely different. But of course, the reason is that it's 1 over m, which is small. And then once it's small, you might as well set it to 0. So we have the flavor symmetry, but we also have a spin symmetry. And the spin symmetry results from the fact that there's no Dirac matrix anymore. If you perform a spin rotation on the fermion field, this spin operator also involves the Pauli matrix, and normally it does not commute with the d slash in the Dirac-Lagrangian. So normally the Dirac-Lagrangian is not invariant under spin rotations, but this one is because there's simply no Dirac matrix here. So it's a flavor and spin symmetry, and it's actually a combined spin flavor symmetry. So it's an SU2 for spin times NQ, the number of different heavy quark species. So realistically for bottom and charm, it's an SU4. If you included the top, it's an SU6, but as I said, there are no top hadrons, so really it's not very relevant for top mesons. And this really means, for example, I can consider a B meson, which is a pseudoscalar 0- state made out of a B quark, and I can consider, for instance, a D star, which is a vector meson with spin 1. And these two states are connected by the symmetry, even though they have different states. One is a pseudoscalar, one is a vector. It's a combined symmetry. Well, for that reason, as I said, it's not just that I can take a B and a B star, or a B and a D. I can also take a B and a D star. So I can do spin and flavor rotations at the same time. It's really combined. Okay. Oh God. I guess that's probably heavy quark number conservation. It's also there, but it's kind of empty. Yeah. Good. So I will not dwell much longer on this, but I will dwell a little bit longer because I want to look at the effect of the first order corrections. Okay, this guy here. So symmetry breaking corrections. And of course, the symmetry breaking corrections enter at order 1 over m. Why? Because there is an m here. So these corrections are going to be much bigger for charm versus bottom, because the suppression is less. And you also see that the gamma matrices reappear. Also, the spin symmetry will be broken by these corrections. Now here, I wrote d slash d slash. You could have said, well, d slash, that's d squared. Why do you write the slashes? Well, you need to be careful there. For vectors, for ordinary 4 vectors, a slash would indeed be a squared. But here we have derivatives. And derivatives don't commute in quantum field theory. So we need to be careful. D slash is the same as gamma nu, d nu, and this gamma mu, you can write as, this is 1/2 the anticommutator plus 1/2 the commutator. And of course, the anticommutator is by the Dirac algebra 1/2. The anticommutator is just a metric tensor, G mu nu. And this thing here is minus I times sigma mu nu, the spin operator. And this is antisymmetric. So for the first term, G mu nu times d mu d nu, that's really what we call d squared. But for the second term, minus I sigma mu nu, sigma mu nu is antisymmetric, so I can write this thing as 1/2 times the commutator of two covariant derivatives. But the commutator of two covariant derivatives, unlike the commutator of ordinary four vectors, is not 0. What is it, the commutator of two covariant derivatives? Field strength, wonderful. Do you remember what the prefactor is? It's minus IG strong times G mu nu A dA. Okay. So you see, we could leave this structure as it is with a d slash d slash. It would be fine, but it's actually nice to split it up into these symmetric and antisymmetric structures. The symmetric structure is simply d squared, and the antisymmetric structure, which is the only one that has a non-trivial Dirac matrix, the spin operator here, comes with the field strength. And then we find that, L effective now to subleading order is H IV dot D H. Sorry, I'm writing again too high. Let me correct that right away. The first 1 over M correction is HV ID soft squared, HV. And the second 1 over M correction is GS over 4M HV sigma mu nu G mu nu A dA HV, and then higher order terms. And what is the physical meaning of these terms? Well, obviously, if you look at this term and you substitute the derivative for the residual momentum, you forget about the gluon for a moment, then this is k squared. And remember, there is a perp here, which I forgot. And the perp in the rest frame is just the spatial component of the vector. So in the rest frame, apart from the gluon, this is residual momentum vector squared over 2mq. And that's simply the non-relativistic kinetic energy, right? You have a particle that's at rest, and now it moves a little bit, non-relativistically, that's k squared over 2m. So this is the kinetic energy. And it's called the kinetic operator or the kinetic energy operator. So it's an operator that also contains some interactions with gluons, but in such a way that it's gauge invariant. It's the kinetic energy, and now you take the momentum and you replace it by the how is that called? Covariant momentum, right? With the gluon field in, and then that's what this operator describes. And the second term here, if you work this out non-relativistically, you will find that this is sigma over 2, the spin vector dotted into the chromomagnetic field. So in analogy to the Maxwell Lagrangian, you can take G mu nu for the gluon, you can write it in terms of electric and magnetic components of the fields. And then when you dot this into a sigma, only the magnetic components survive. And this is a coupling, if you like, of the heavy quark spin to the chromomagnetic field. Okay, so we see that both operators violate the spin symmetry. So they violate the spin symmetry. And this guy also violates sorry, they both violate the flavor symmetry. I'm sorry, both violate the flavor symmetry because of the 1 over m factors. And this guy also violates the spin symmetry. So we see that it doesn't cost much. We just need to go to order 1 over m, and all the symmetries are broken, in analogy with light flavor SU3, where as soon as you include the quark masses to linear order, also the flavor symmetry is broken. Okay. And now people have derived the consequences of these symmetries. I don't want to spend too much time on that. Let me just tell you that there are some nice predictions that one can do. So for example, you can take the mass of the spin 1 state B star and the mass of the spin 0 state B. How do you get from a B to a B star? Well, all you need to do is to flip the spin of the heavy quark. If the stuff around the heavy quark, let's say, has spin up, and the heavy quark has spin up, you get a spin 1 configuration. If you flip the spin of the heavy quark, you can get a spin 0 configuration. So the two states are connected by a spin transformation. And the leading Lagrangian is invariant under this. So these two states have the same masses to first order. But then this operator violates the spin symmetry. Okay, and it's the spin symmetry that connects these two states. So basically, these two states get a correction from the kinetic operator. And the correction starts at first order in 1 over m. So for instance, you find this prediction that these two masses should be almost degenerate except for terms of order 1 over mb. Actually, experimentally, this is good to 1%, this relation. This is actually very good, compatible with the heavy quark limit. You can be more precise. You can, for instance, look at the spin splitting in the charm sector compared to the spin splitting in the bottom sector. Again, the masses would be degenerate if it was only for the first term. The breaking starts at order 1 over mq, but now the breaking here in the numerator starts at order 1 over mc. The breaking here starts at order 1 over mb. So you predict that this should be approximately mb over mc, which numerically is something like 3. Experimentally, as I said, this is 1.01. This is 142 MeV over 46 MeV, sorry, which you see is very compatible with a factor 3, and so on and so forth. There are other predictions. So for instance, you can also compare the masses of baryons with the masses of mesons. Now, baryons and mesons are not connected by a spin transformation. They are completely different bound states, okay? Nevertheless, the mass of the bound state is the mass of the heavy quark plus the mass of whatever the rest is. And whatever the rest is independent of the quark mass. That's what this first line says. So for instance, you would find that up to corrections, this first line should be the same in the charm system and in the B system. And again, this all works empirically very well. All these relations are very well satisfied. So, but I will not really spend too much time on phenomenology. I want to come back to the hard gluons. We started a quarter past or something, right? I somehow, yeah. Wanted to come back to the...
One of the issues got 90s where this was far bigger than the observed number, hyperfine splitting between the system and the system, or maybe
No, I think in the spectroscopy there were never issues as far as I know. but we can look it up later if you like. Wanted to come back to the hard gluons. So basically, when we derived this, we simply forgot about the hard gluons. We said we are only interested in the soft interactions of the heavy quark. Now, what about hard gluons? The philosophy is always hard gluons in QCD are perturbative. So we can always account for hard gluons in the form of Wilson coefficient or so-called matching coefficients, right? And maybe Anish mentioned that this morning, maybe he didn't. So when you construct the effective theory, the effective Lagrangian is an expansion in terms of operators times Wilson coefficients, and the Wilson coefficients contain the physics of all the short distance degrees of freedoms that have been integrated out, including the hard gluons, okay? So we should go back to this Lagrangian and start asking the question, at what point could we add Wilson coefficients to the operators which would account for the hard gluon corrections? Now, the leading Lagrangian, such as this one, we could put a Wilson coefficient, but you can always immediately rescale the fields to put this coefficient to 1. So normally we say we use fields that are canonically normalized, which precisely means that the coefficient here is 1. So for this leading term, we cannot do anything. But in principle, we can do something for the subleading terms. So in principle, the kinetic operator or the chromomagnetic operator, they could have non-trivial Wilson coefficients, except it actually turns out the kinetic operator, so normally people then would write coefficients here, C kinetic and C magnetic, okay? It's actually what they're really called. Except one finds that C kinetic is equal 1 to all orders. And the reason is another symmetry invented by Anish that's called reparametrization invariance. You can show that in the construction of this HQET Lagrangian, there is some ambiguity as to how precisely you define this reference for velocity vector. I mentioned it's the velocity of the heavy meson, but you could have asked me, well, you know, what if I choose it a bit different? Just an epsilon different, would it really matter? And of course, it doesn't really matter. These things should be invariant. Physics should be invariant under how exactly you choose this reference vector. And that has a powerful consequence. And one of the consequences is that you can prove that this coefficient of the kinetic operator is 1 to all orders. And it's not so surprising because, you know, in momentum space, this is the energy. In the rest frame, v dot d is just a zero component of the derivative is the energy. And this is the non-relativistic energy. And, you know, we should not change the Einstein relation between energy and momentum. So the fact that the energy is given by k squared over 2m with a coefficient that's 1 should not be changed by quantum correction. And that's the physics reason why this coefficient is 1. C magnetic, there's no reason why it should be 1. And in fact, C magnetic is not 1, it's 1 plus order alpha. And I can give you the explicit form. It's 1 plus alpha over 4 pi minus Ca log mq squared over mu squared plus 2 Ca plus Cf plus order alpha squared. The one loop term was computed by Eichten and Hill in a paper also in Physics Letters B 1990. And this is an example of a non-trivial matching coefficient that arises when you account for the effects of hard gluons. How would you perform the calculation of this matching? Well, since we're dealing with hard gluons, we use perturbation theory. We use so-called perturbative matching. And I'm not going to do the calculation, but I tell you what you would need to do. You would need to choose some Green's function, some amplitude that is sensitive to this operator. Now, what does this operator do? It has three fields, a quark, an antiquark, and a gluon. So the amplitude we look at needs to contain at least a quark, an antiquark, and a gluon. That doesn't uniquely define the amplitude. I would choose the 3-point amplitude with a quark, an antiquark, and a gluon. You could also choose an amplitude with a quark and an antiquark and 5 gluons. Fine, up to you. You would get the same answer, but you would calculate longer. People have checked this. I mean, people did these matching calculations with not the simplest amplitude, just to make sure that everything is under control and confirm that you get the right result. But the simplest way of getting it is to really look at a 3-point function. You have a quark coming in, a quark going out, and a gluon going out. And you take this amplitude in the full QCD theory. So really, QCD with all its features. And then you say that the answer of this calculation should be equal to some coefficient C magnetic times the corresponding 3-point amplitude in HQET. Where now I have my quark with velocity v, double line notation, and again a gluon. And I'm looking at a transversely polarized gluon because this is what I need here. Otherwise, I would also, I need to, okay. You have also this contribution and this contribution, but you will get both from this calculation. But here what And basically you insist that these amplitudes should be the same up to terms that are down by 2 powers of 1 over mq. And now you compute this at tree level and at tree level, where you just have the vertex here. And then if you do, you have to do the calculation on both sides, use the on-shell conditions, use the relation between momenta in the effective theory and the full theory, etc., etc. You will find that tree level C magnetic is 1. When you do the one loop calculation, you'll do some loop graphs here, you'll do some loop graphs here. You will find, oh, they don't give the right result. Even the logarithmic terms are not the same, and then you adjust this coefficient so that the result matches, and that's how you get this. Because what you compute here is only the soft gluons. In HQET, by definition, we only have the soft gluons. This guy accounts for the hard gluons. And of course, in QCD, we have both. We have hard and soft gluons included, right? So we need this term to account for the hard gluons. Okay, but I'm not going to bore you with this because we'll do such calculations in the context of SCET a little bit later, but it can be done and it has been done. Good, I want to use the remaining time to do a few things which would not be strictly necessary to do, but which are very useful to do, both from a EFT point of view and also from the point of view of moving over to soft collinear effective theory tomorrow. So we'll take this heavy quark effective theory Lagrangian, which hopefully you agree. Maybe it's a bit strange, but it's relatively simple. And I will apply some standard EFT things which we'll need later for SCET. The first thing is to assign power counting. And this I'm sure Anish has discussed or will discuss also in the context of the Carrel Lagrangian, because he has done a long time ago, very profound and pioneering work on this. So it's nice in an effective theory to, you identify a parameter, which is the small parameter in which you want to organize your expansion. In the case of HQET, this small parameter is the ratio of lambda QCD over MB over MQ. And let's call this little lambda, okay? And all we need to know is that this little lambda is much less than 1, and we want to organize our expansion in terms of little lambda. And now we try to, for all dimensionful quantities in the game, we try to ask the question, how do they scale with lambda? Do they scale with lambda? And if, how do they scale with lambda? Okay? And we'll assign power counting, in particular, to all objects in the Lagrangian, including the fields. Then there's something called naive power counting, where you say everything that has a dimension in the low energy theory should scale like, lambda QCD to that appropriate dimension because the mass has been integrated out. And there's something, this is naive dimensional analysis and the power counting of naive dimensional analysis. And for HQET, this is what we will find from this discussion. But this is not always the case. The chiral Lagrangian is an example where the power counting rules do not follow from naive dimensional analysis, and SCT likewise. But what do I mean by this? Okay, so the first quantity I want to study is the residual momentum K. Now, remember, we separated the heavy quark momentum in NQ times V plus K. The first term obviously scales with the heavy quark mass, but the K, we said, is a soft momentum which scales with lambda QCD. So if I normalize K to the heavy quark mass, then this scales like little lambda. Lambda QCD over MQ. So in other words, I could also say that K mu scales like lambda times MQ. And what is important here is that it's linear in lambda. Lambda is dimensionless. When something has dimension, I will always write it as MQ to the appropriate power times powers of lambda. So K is linear in lambda. And that means in the effective Lagrangian that derivatives, ordinary derivatives, I will assign power counting lambda, because ordinary derivatives give powers of K, and powers of K means powers of little lambda. I could also write MQ here, lambda times MQ, but all I care about is the counting with lambda. Okay, now what about, what else is there in the Lagrangian? Well, there's the field. What about the field? We have derivatives, we have fields, and we have gluons. So we'll go through all of them. What about the field, little h? Now, in general, to derive the power counting for quantum fields, if they are interacting fields, is not a trivial thing. If the interactions are strong, if the interactions are small, perturbative, then it is a trivial thing. So for small interactions, for perturbative, let's say, perturbative interactions, I can start from the propagator, okay? I simply look at the propagator. Propagator is the time ordered product of two fields. Evaluated between the vacuum. I go to momentum space, write this as d4k over 2 pi to the 4, e to the minus I k dot x, I divided by v dot k plus Feynman I epsilon. And now I have residual momentum here, 4 powers of it. So this will scale like lambda to the 4. I have an inverse power of residual momentum here. So this scales like 1 over lambda. And the exponential never scales. The exponential tells you, so k, of course, scales like order lambda. But essentially, that tells you that the relevant x values for which this two-point function takes values that are not exponentially suppressed is x of order lambda to the -1. So the exponential never contributes to the power counting, just gives you the relation between k and x. But here you see we have 4 positive powers and 1 negative power of lambda. So this two-point function scales like lambda cubed. And it's a two-point function of the field. So from this, we assign perturbative scaling HV of order lambda to the 3/2. And again, if we take this HQET to a limit at low energies where it's completely non-perturbative, in principle, the scaling could be modified, but in the free theory limit, this is the scaling we can associate with the field. Yeah, well, in some sense, good point. We'll come back to that tomorrow when we talk about the method of regions. Excellent question, yeah. So, of course, I'm integrating over all of momentum space here. But on the other hand, I know that this is a field describing soft quantum fluctuations. So if you wish, in your mind, you can think that you restrict this integral to a volume V soft, which is a ball in 4-dimensional momentum space of momenta not exceeding a certain upper value. In principle, that's what you should do. In practice, that's not what you do. In practice, we will never introduce cutoffs. We will always work with dimensional regularization, and it's the method of region that tells us whether an integral gets a contribution from the soft region or the hard region. We'll discuss that next time. But if it helps you conceptually, since these fields are restricted to soft Fourier components, one should consider putting a cutoff here, defining a sphere in momentum space that restricts this to soft momenta. Yeah, very good point. The last thing we have here is the soft gluons in the Lagrangian. Here we go. And we'll do the same thing for the soft gluon. We'll look at the two-point function. A mu A, A nu B, soft between the vacuum. This is the gluon propagator, so we get D4K, 2 pi to the 4. Again, B soft if you like. There's also an exponential, which I forgot in the notes. I'm sorry for that. And then we get a Kronecker delta for the color indices. And the gluon propagator is k squared plus I epsilon. And then in arc-C gauge, we have G mu nu plus the gauge dependent terms K mu, K nu over K squared. Again, this counts like lambda to the 4. This counts like lambda to the -2. And here you see there are no powers of K, and here 2 powers up, 2 powers down. So this whole bracket doesn't have any scaling with lambda. So this thing goes like lambda squared, which means the soft gluon field scales like order lambda. And now in each case, this is exactly what naive dimensional analysis would tell you. The fermion field has mass dimension 3/2. So if by the logic that you say in the low energy theory, that must be 3/2 powers of lambda QCD. That's exactly what this relation tells you. And the gluon field has mass dimension 1, and it scales like lambda QCD. So this is naive dimensional analysis in the case of HQET, but again, we'll see that in SCET this is not the case. What is important, and what will also be the case in SCET, that it's essential that the soft derivative and the soft gluon field have the same scaling, because from here and here, it follows that the covariant D soft scales like lambda. And if that was not the case, we would break gauge invariance by the construction, right? We would have a different power counting for ordinary derivatives and gauge fields. That would be bad in a gauge theory. We would break gauge invariance. We definitely don't want to do that. Good. Now I need to, how do I clean the board? Is there a wiper or this? Oh, wonderful. Good. Any questions while I erase the board? Yes.
Then it just looks like e to the power 8 pi square by d square alpha sum, right? So the brilliance of that is that even though alpha s is large, your power counting parameter is e to the power minus 1 over alpha s, so that still gives you a good control. So even if alpha s at m.
Yeah, but this is alpha in the low energy
alpha
region, right? Yeah.
Right. Even if that
Alpha is at MQ,
right,
of course,
like,
is.
even if it becomes large, it still gives you a solid power counting because you exponentiate it.
Yeah, you could say like that. I should say one thing. I derived the power counting here from the leading order Lagrangian. You could now go back to the next two leading order terms, and if you do this carefully, you will find that the next two leading order terms indeed are suppressed by an extra power of lambda compared to the leading order terms. So this is consistent. I have done it with the leading order Lagrangian, but it's true also for the higher order terms. So in other words, this, where is my Lagrangian? Here. So if I take this Lagrangian from up there, I will find that this term here is order lambda to the 4. Yeah, lambda 3/2, lambda 3/2. These terms here are lambda to the 5th. And when you integrate the Lagrangian over d4x to get the action, you lose 4 powers of lambda, so the leading term is lambda to the 0. That's the leading term, and the power corrections are lambda to the 1st, lambda to the 2nd, and so on. So it's a consistent expansion. You have some details here in the notes. I want to discuss one more point. That's called the decoupling transformation. There's something not usually discussed in the context of HQET, but it's profoundly important in the case of SCET. So if I take the leading order HQET Lagrangian, once again, HV I V dot D soft HV. It's an example of a Lagrangian where the coupling to gluons is entirely through a reference 4 vector. In this case, the velocity vector, v mu. So gluon coupling via a 4 vector. Not a Dirac 4x4 matrix. Whenever you have such a Lagrangian, this coupling can be removed by a field redefinition. And And the field redefinition is the following. You take your field little hv of x, and you write it as an object that I will define, I will call S sub v of x times a new field hv0 of x. So I simply do a unitary field redefinition. I take my, you could invert this, right? H0, the new field, is S inverse times the original field, and S is a unitary matrix, as you'll see in a moment. So this is the new field, and this is the old one. And what is this S? This S is defined in the following way. SV of x is a so-called soft Wilson line. It's a path-ordered exponential of I times strong coupling GS, a line integral from minus infinity to 0. And now the gluon field dotted into precisely this 4 vector that sits here in the Lagrangian. And the field now integrated along the velocity direction, x plus v dot t, from 0, which is just x, out to minus infinity in the direction of the 4 velocity. So this is a unitary operator. And it's called the soft Wilson line. And if this is the point at which the field originally sits, this is an object now that goes from here out to minus infinity along the direction of v mu. So it's really a line operator. And we call this a time-like. It's a time-like Wilson line because v mu is a time-like 4 vector. It squares to something positive. And this symbol P means that, you know, these are gauge fields. They are 3 by 3 matrices in color space. So if I were to write color indices, I would have a color generators here. So this is a 3 by 3 object in color space. And therefore, we need to order these objects in order to define the exponential. And this is such that, this is such that fields closest to t equals 0 stand to the left, and then the further you go away from the origin, the fields are ordered in that direction. Is this what? Yes, it is. Yeah, okay, so this is a tangent now to my discussion, but in the context of HQET, if you would do a reparameterization transformation here, which I did not discuss, this object would transform into itself plus something that's 1 over m suppressed. And then usually this reparameterization invariance in the context of HQET gives you connections between leading order operators and subleading order operators. So at subleading order, you would have to be careful with the transformation of this Wilson line. But at this point, I'm just interested in the leading order Lagrangian. So this object has the following property, and this is another exercise I recommend. The exercise is to prove that what I say is true. And the property is very simple, that if I take v times an ordinary derivative with respect to x, acting on this soft Wilson line, you get minus g v dot a soft of x times the soft Wilson line. And if you bring this term to the left-hand side, you see that this plus this combines to give combines to give a covariant derivative. So then you find that I v dot d soft acting on the soft Wilson line is equal to 0. So in other words, if we have a Lagrangian where the gluon coupling comes through a 4-vector, we can always define a Wilson line such that it satisfies this equation, that the same differential operator that stands here acting on that Wilson line, where the Wilson line is defined with the same 4-vector, gives 0. Okay? This is a cool trick. Don't forget this trick. It's absolutely cool to know this trick. Because you see, if you now look at this filter definition and you plug it in here, what happens? I have this derivative acting on S, but then it gives 0. And then I have the derivative acting on the new field. Okay? But the gauge part, I only have once, of course. So this is a derivative plus a gauge contribution. The derivative acts on this and this. The gauge part, I have only one. So the gauge part is already eaten by this term. So when I move this covariant derivatives through the Wilson line, only the ordinary derivative remains. Okay, so my LHQT now, in terms of the new field, is HV0 of x, I, and now just an ordinary derivative. HV0 of x. No gluons anymore. When I add this here, basically, so I'm basically, you could, so I'm using that I v dot d sv of x hv of x. It has two terms. It has the term where this acts here, which gives 0, and then it has the term where the derivative part acts here. So then this becomes hv of x I v dot del on hv0, and now this guy cancels against the s that is contained in the h bar. So the Wilson lines cancel out, no gluons, a free Lagrangian. This is a free theory. Now you say, oh, wait a second. What does that mean? Something happened. I start from QCD, I derive my heavy quark effective theory. It describes nicely how gluons interact with heavy quarks. Now I do field redefinition and I get a free theory, no gluons. Sounds like something got lost under the carpet, no? So this looks like a puzzle, but it's actually not a puzzle. Okay, this just means that I can choose a field in such a way that this, this heavy quark seems to not anymore interact with gluons. But the question how heavy quarks interact with gluons is not a physical question. The question is how heavy quarks interact with other fields around them. So really the right way of interpreting the statement of this Lagrangian is to say heavy quarks interact like soft Wilson lines. So for instance, if I want to understand how a heavy quark interacts with a light quark, for example, I look at a term in the Lagrangian which has, let's say, a light quark, a gluon, and a heavy quark. So this could describe an interaction in the B meson. Now, let's say I do this field redefinition, and then what remains is I still have the heavy quark, I still have the, let's say, the soft gluon. And now I get my Wilson line, SV, and then I get this field SV0, and this field SV0 really has no interactions anymore. It's a sterile field, it doesn't do anything, doesn't have any interactions, but you see that the light quarks and gluons, whatever I write in this operator, whatever probes the heavy quark, now it doesn't interact with the heavy quark anymore, but it interacts with this Wilson line. So really what this means is whatever light stuff you let interact with the heavy quark after the field redefinition, that heavy quark is gone, but the Wilson line is there, and the light stuff sees that Wilson line, okay? So, you know, this is, I think I'm running out of time now. Maybe I stop at this point. I had about half a page more, but I can also cover that tomorrow. It's okay. This is an important point, and maybe it's confusing at this point. But the idea that, you know, the soft interactions of heavy quarks can be factored off in Wilson lines, and really you can think of a heavy quark as just being a Wilson line. This is the nicest way of thinking about the flavor symmetry, because the Wilson line doesn't know whether it comes from a quark field or a scalar field or a vector field. It only knows it comes from an infinitely heavy field. That is a color triplet. That's all that matters. For the Wilson lines, all that matters is this is a Wilson line in the fundamental representation because there was a heavy object transforming under SU3 color in the fundamental representation. And so in that notion, the spin symmetry is even more obvious because the Wilson line is just a string operator. It doesn't carry any spin, okay? And in the context of SCET, we'll have a similar discovery that also the soft gluon effects will be through some reference 4 vectors to the different other fields in the effective theory. And this decoupling transformation, as it's called, where you go over to a new Lagrangian where the fields do not have soft interactions anymore, and then at the expense of getting Wilson lines in the theory, that will be the basis of deriving factorization in the context of SCET. So in the context of HQET, this is just a curiosity. It's not particularly useful for much. It's useful for one thing, which I didn't have the time to discuss. We can discuss tomorrow. But in the context of SCET, this exactly same trick will come back and have very useful consequences. This is the reason why I wanted to show it to you. But I think I'm out of time, so maybe for today we call it the end of the lecture, and then we briefly finish this discussion tomorrow. But then for all lectures, right? The discussion is for all lectures, okay. Hmm? Yeah, so I think there was a paper, I think it goes back to Edward Churyak, where it's written, heavy quarks behave like cannonballs. So, you know, once you have a heavy quark in motion, it flies by you, and we are the soft gluons, we try to interact with it, we cannot really change its motion very much. Right? We can change it an epsilon, but it basically will just keep flying, keep flying. So for velocity, v mu, v square equal 1, this is a time-like reference vector. And in particular, you know, if you go to the rest frame of the heavy quark, V mu is just the vector 1, 0, 0, 0. So it's just a time, it's just a unit vector in the direction of time. And in that case, this Wilson line would be a temporal Wilson line, right? It would be the zero component of the gauge field integrated over time. So this is also why we call this T here, usually, because it's something like a time. So it's time-like because the reference vector is a time-like reference vector. In SCET, the Wilson lines we will encounter will be light-like, and the reference vector will be a vector that squares to 0, not to 1. That is the main difference, as we'll find out. We'll not be dealing with time-like Wilson lines, we'll be dealing with light-like Wilson lines, but that is the only difference as far as that point is concerned. Time for break. Oh, sorry. Yeah, whatever light cone OPE is. I mean, the sort of the rigorous definition of the operator product expansion really relies on Euclidean space. I mean, really relies on the fact that when two objects have a delta x square which goes to 0, it really means the two things come together at the same point. So it's an expansion in local operator, and it's a generalization here where, as we'll see, not in this case, in HQET, everything is local. Everything is local, as you could see here, right? These higher dimensional operators, they're all local operators. It's an infinite string of local operators, like in this MEFT. In SCET, the operators will not be local. They will really be non-local on the light cone. You will have fields, different fields together at different positions, but the positions are not infinitely close to each other. The positions satisfy x minus y squared equal to 0, but not x equal to y. But rather, they can be far apart, but on the light cone. Yeah, but not on the light cone. Yeah, but again, for light-like separation, you can't do that, right? Because for light, there's no rest frame. You can never go to. And you can worry that you were taught in QFT that the only consistent QFTs are local, because otherwise you violate causality and all these things. We can come back to these questions. I mean, in these effective theories, the theories are non-local. It's not a contradiction to causality and unitarity and all these theorems. Of course, the underlying fundamental theory is still local, but the effective theory can be non-local. And we'll in particular see how gauge invariance is maintained despite the non-localities, and the Wilson lines will play a key role in that regard. But that's the stuff of the remaining 3 days, so I need to discuss that now. Any kind of meson decays, yeah. No, I guess the true answer is you can't really see it from here because I didn't discuss the details. I mean, you could discuss, for example, from what we have discussed today. We can do that in the discussion session if you like. I can give a few more details, but what we could do directly is a so-called heavy-to-heavy decay. So for instance, a decay B meson to D meson plus muon neutrino. So let's say a B minus to D0. This would be at the quark level, a transition of a B quark to a charm quark plus a lepton neutrino pair. And these people would be interested because this is proportional to the VCB matrix element of the CKM matrix. This is something we could discuss now because basically this quark level transition is described by a current operator of the charm quark to the B quark. So what we would need to know here is typically form factors defined by, let's say, D meson with some momentum PD, and now a current gamma mu 1 minus gamma 5 B, and a B meson with some momentum PB. So you would have to know these kind of hadronic matrix elements. That's the big challenge. And one way to get this is computed on the lattice, but one way to get this also is apply heavy quark effective theory, where you would describe the B quark and the charm quark in the effective theory. You would describe this current by, an effective current for the charm quark, HV prime, let's say, gamma mu 1 minus gamma 5, an HQET field for the B quark, HV. You would describe these states in heavy quark effective theory. And for instance, you would be able to show that this type of matrix element at the end of the day, even though they define many form factors in QCD, they're all defined in terms of a single function of the product of V dot V prime, where the function, even at the point where the velocities are the same because of heavy quark symmetry, must be equal to 1. And this is also one of the ways in which VOB was determined, that one measured experimentally this form factor as a function of V dot V prime. It looks something like this. And you kind of extrapolate it to the point where V dot V prime is equal to 1. And what you measure here is the product of VCB times this function. This function is called the IISc function. And knowing that it's equal to 1 at this point, you can read off what VCB is, very roughly speaking. This was the first application of this heavy quark symmetry. Then, of course, there are corrections, 1 over m suppressed. People have studied these corrections, tried to estimate them. But this is an example of how you could put this to work. Right? You have 2 heavy mesons. For both of them, you can use heavy quark effective theory. And then basically the symmetry principle is that you know that this form factor at point of equal velocity is normalized to 1. But okay, I mean, we could spend the whole course on applications of HQET. I won't do this really. There's also many, of course, there's many lecture notes that you can look at where this is discussed in detail. It's not that HQET can do, you have to be careful. This type of heavy-to-heavy meson transition, it's fine. If this was a pion, for example, it would not work anymore. You would need soft collinear effective theory, actually, because the pion would have a very high energy. It would more be a light-like particle more than a heavy meson bound state. So it's not that HQET applies to everything. And then, as I said, if instead of doing an exclusive decay, you look at the sum over all hadronic possible final states, so-called inclusive decays, this is work by Anish and others, then it's a different type of the heavy quark expansion. It uses HQET, but in a somewhat different context, where you look at actually using the optical theorem, something you learned this morning in the class on dispersive methods. Using the optical theorem, one can turn these inclusive rates B meson to B meson correlation functions, which can be calculated then using heavy quark effective theory. So it's just it's a tool, but to apply the tool is also an art form. You have to understand really which method to use in what context. Good.